Hello, everyone. Due to popular demand of literally one person saying, "Hey, I like these. Keep doing them," then I'll keep going through lectures of these chapters. This is chapter 19. This is Our Galaxy, and we're kind of doing this the way we do all the other stuff. All right, so when we talked about the planets, we talked about the Earth for a bit, and then the other planets. When we talk about stars, we talked about our star and then compared to other stars. And so we're going to talk about our galaxy and then compare to other galaxies. Um, so it's not too bad. What's in front of you right now is a beautiful sort of image of the center of the galaxy, and you can see it's chock full of stars and gas and dust. If you looked out at night, this might be what you would see, right? This image, it has a comet in it. Let me see if I can pull up the pointer. I should have did this first. There we go. It has a comet right here, and whoa, that's not what I wanted. And down here, there's this stream of gas and dust. If you go out and look tonight, you if it's really dark, you can see it's kind of a faint haze, unless it's like super super dark. All right, these are all going to be fairly, long exposure images like this. But you go out and you look for a while, and you'll see something that looks like this. That's the galaxy. In particular, what we're seeing is dust and gas that's absorbing light from stars behind it, and uh, it's blocking the light. So we see an obvious path. And the other thing that we see is lots and lots of stars, because in the direction where the stars are, that's where we're going to see this sort of extra bright streak. Right. So this is the whole sky. If we could see the entire galaxy, the center is right in the middle, and there is lots and lots of gas and dust and lots of stars. Here's the view in um, radio waves. There's lots of stuff coming from the center of the same image. Here it is looking at hydrogen, so this is microwaves. Here it is. This is also in radio wave. This is even lower radio waves. This is getting close to your FM radio. Close. The microwave background and uh, the radiation coming from the galaxy here. Here it is, an infrared, more in infrared. A different view. Um, another view of the Milky Way. Another view. Again, I put in a lot of pretty pictures, and I think they're good, but I'm also trying to build up. All right, now we're seeing what's being produced in X-rays, and there's some streaks in this that aren't real; they're data artifacts. But you can kind of see the brighter areas are where there's more energy. There's more light being produced in all wavelengths. And here it is in gamma rays, and you see the same sort of thing. And there's some extra bright sources in gamma rays, and we're not sure why. So all of those pictures had some stuff in common. We should have seen everything edge on, and that's how we see it because we're in it. Right? Is if we could see it like we see other galaxies, we may be able to see it from above. But because we're in it, we have to infer things looking at an edge on view. And what we see is that there's a disk of stars with several arms. We're sitting somewhere out near the edge of one of the arms. There's a bulge that is higher density stuff There's a halo, which contains lots of globular clusters and uh, other older stars. And, the relative sizes, it's about 1,000 light years thick and 100,000 light years in width. And here's a view of it in infrared. A lot of these, I'm just throwing stuff out there because I'm not, I want you to see as much different info as possible. So this is an artist rendition. Obviously, we can't possibly get this image, but we can estimate what it would look like from looking at other galaxies and from what we can infer from being inside. And we figure our galaxy, the Milky Way, has spiral arms. And you can see what it kind of looks like a hurricane swirling. But there's a bulge, there's a halo around it, and there are spiral arms. And you'll notice a few things. The bulge is a lot redder than the spiral arms are. That's going to make sense here in a little bit. So there's a better image of this out there somewhere. I can't find it. There's a set of arms, and some of them are more prominent than others. But we can deduce that there's about four, maybe five. There's 4 or 5 distinct areas where there's high densities of stars. And the bulge here seems to have a sort of longitudinal shape. It's lozenge shape, not spherical. So it's kind of this will be what we call a barred spiral eventually. Right. And some of the things we can point out, we're in this small little spur between two arms, what's called the Orion Spur. It also holds a bunch of the nebulas we can see easily. And so this image points out a few of the different things that we can see. So a lot of the stuff we just have to infer is that there's other stuff around it. We kind of infer the presence of, but there's a lot of stars in a way. In our galaxy, there's a number of different orbits going on. Right? We have a disk, and we have a bulge and a halo. In the disk, everything orbits like a small flat disk. Physics for forming a galaxy look remarkably similar to forming a star or forming a solar system. You're going to have gas and dust collapse inwards, and the angular momentum is going to cause it to form a small flat disk. And so most stars may be slightly above or below the center of mass of the disk, and they'll oscillate so they'll orbit in the plane of the disk, but they may have some up and down motion. Basically, because if they're above it, the disk is going to pull them down, and if they're below it, the disk is going to pull them up. And once they're crossing through the disk, they have velocity, so they keep going. So you'll see this sort of undulating effect in many of the stars. Right, and that's the thing, we can't. This sort of orbit, like for the sun, this sort of orbit would be 230 million years. So we can't really infer. We've not seen for enough time one of these orbits to see an oscillation. We kind of have to infer that some stars are moving upwards, some are moving downwards. It makes sense that they're going to oscillate like this. They're not going to escape. Now, in the bulge and the halo, what's happened is as the galaxy formed, these bits of the cloud formed clusters before everything flattened out. And so these orbits are going to be completely random. It's whatever way the bit of the cloud was moving first. And it also depends on if they have any gravitational interactions. But essentially, these things are left out of the disk and can just orbit in any direction they want. So these are analogous to long period comets. They don't come into the solar system, they just orbit around in a big cloud in random directions. The the these stars are very old and very far away from the disk and orbit in random directions. So we have another image of this here of, you know, this is what's in your textbook. So you can see what we're talking about with that funny image from before. Um, we can deduce, right? We're just applying Kepler's third law to the entire galaxy. And when we do that and measure the velocity of the sun relative to the galaxy, what we figure out is that there's almost 100 billion solar masses inside of the sun's orbit. You can't figure out anything beyond outside the sun's orbit, because Kepler's third law doesn't work like that. You have to it has to be the mass that's attracting, which is inside the orbit. And so this gives us an estimate of the size of the galaxy. It's on the order of 1 trillion solar masses, probably, or under that. It's 10 to the 41 kilograms. That's a lot. There's 41 zeros there. So, um, when we figure this out, this is coming from Kepler's third law and from circular motion. Is this adding the things together gives you a formula for the mass in terms of the velocity we can measure and the radius we can measure and the gravitational constant. And so we can do this for all sorts of galaxies. And we are going to, we're going to look at where people have done that and what they found out. So I hear people coming up. That's weird. So uh, we have formation of stars in the galaxy. There has to be a bit of churning of the stuff, right? A star supernovas, and then the stuff is just kind of around it. And we'd like to know how new stars are forming and how the stuff's spreading around. And there's a recycling cycle. Right? There's stars forming, and then they become supernovas, and they spit new, or they become white dwarfs. And they spit new gas out, and that reseeds clouds, and so the clouds reform. And we start with a supernova, or with a hot star blowing off gas, right? And you can see the bubbles of gas being blown outwards into the interstellar medium. And low mass stars are going to make planetary nebula and stellar winds. And high mass stars are going to detonate, they're going to supernova. And so you get your heavy elements from the supernovas. And as the remnant cools, you start to see it in visible light. All right. So when it goes off, it's going to radiate at X-rays and gamma rays. But as it cools, you'll start to see the remnants in visible light, and it'll continue to cool down. Right. Eventually, you'll see, um, uh, you'll see other forms of radiation. Right. Radio emission will occur because you're taking charged particles and you're accelerating them at high speeds. So one thing that will tend to happen is you'll have clusters of stars form, and so you'll have supernovas occurring all at a similar time in the cluster's life. And so they'll create larger and larger bubbles that will effectively expand, blow out. And so you'll get a cloud of dust that will spread out. And so it'll recede more area in the disk as this cloud of dust rains backwards. So as this material cools, first it deionizes. You end up with atomic hydrogen. And then it cools further and you get molecules of hydrogen. Right? And you'll get molecules of other stuff as well. Right? But just generally, in these stages that it goes through, there's the remnant, and then it cools to atomic hydrogen, and then it cools to molecular clouds. And we've talked about molecular clouds. Right? We talked about the ones in Orion. what they look like. Here's some pictures of them. And eventually that cloud contracts because it's cooled a large amount. It forms a star, and then once it forms a star, that new star will go on and produce more heavier elements and give them off. And so that's a cycle it'll go through. This is what's called the star gas star cycle. And you can see the effects from these things. All right, so here's a summary of it. All right, the bubbles of gas will be at something like 1,000,000 Kelvin. As it cools, the atomic hydrogen will be from 100 to 10,000 Kelvin. And in the molecular clouds we've discussed before, it's 10 to 30 Kelvin, and then the stars reform. And you can see this in lots of uh, emissions coming from different